Hi everybody! In this video I'm going to address the topic of automatic irrigation and soil moisture sensors. I will use the Hydrosys 4 system, which is based on an open source software that is running on Raspberry Pi and some other components. The design of the software is made to use inexpensive components, so to make it affordable. In the first part of the video, I will give an overview of the soil moisture sensors and how to connect them to the board. In the second part of the video, I will address the sensor calibration and the configuration of the automation for irrigation. So now let's have a look at the soil moisture sensors. The first sensor is a resistive sensor. It means that it tries to read the soil resistance by direct contact of the probe with the soil. This sensor is very easy to find on the market, it's very inexpensive, but I do not recommend to buy it for the following reason. First of all, the probe is made with a very thin layer of metal printed on a circuit board that is very easy to corrode. Then it's always in direct current, and this accelerates even more the corrosion. Then we have also this circuit together with the probe, and this is a comparator. You can see there is also a screw that you can use to change the threshold, and it's just made to provide a digital output that is just on and off, depending whether the soil resistance is above or below the threshold. Then this also has a digital output that more or less gives a tension that is proportional to the soil resistance. This sensor has all this problem, and it also not so accurate in the reading, and I have to say, as all the resistive sensors, its reading is very dependent on the temperature. This is a capacitive sensor. This is very easy to find on the market, and it's also quite inexpensive. It tries to measure the soil humidity by measuring the capacitance of the soil. In particular, the dielectric property of the soil, which can be directly related to the humidity in the soil itself. The capacitive sensor readings are quite stable. I tested for some time with good results. The only problem that I have with this type of sensor is that the electronic is exposed. As you can imagine, in a real-world irrigation system, there is a lot of water going anywhere, so it's easy to destroy the sensor. That's why I find a way to coat to protect this circuitry when I use it for real application. Next we have this one. It is just a probe for resistive measurement of the soil. I made it with stainless steel rods. I have to say I use it for a couple of years, and there is no corrosion indeed. This one is meant to be connected with the automation board, which has a particular circuitry. I have seen many bad reviews about resistive soil moisture sensors, so I would like to spend a few words about it. As I use it for a couple of years, I have to say that yes, many sensors that you can find on the market corrode very fast, so are kind of useless. I have to say also that the resistive measurement, even if it is quite stable, is not accurate, and it depends a lot by the temperature. All in all, in the real field, we can afford to have some inaccuracy, and for what I have tested so far, the resistive sensor can be good enough to build an automatic irrigation system. Then we have this one. This is also a capacitive sensor. Indeed, this is not sold as a sensor, so I had to modify the firmware inside the microcontroller to make it work. And currently I am testing it. I had a few issues with the I2C connection, so I made it more reliable. It seems it's working very well now, so maybe in the future I will make it available for sales in my shop. Now let's see how to connect the sensors to the automation board. Okay, I will not connect the relays because for this demonstration it's not necessary. But anyway, there are other videos in which I show how to connect it to the board. So let's take the board and have a look at the analog inputs. Okay, the yellow one is analog input from 0 to 5 volt, and you can see they are labeled as AN1, 2, 3, and 4. So this one is 4, this one is 1, and can be used to be connected to the analog output of the sensors. We have also this row of connectors that is I2C, and we can use to connect the digital sensor. Connection is very easy. For example, we can see that the capacitive sensor has 3 wires. Red and black are for the power, and yellow is for the analog output. So we just need to connect in this way, so that we have ground to the black, plus 5 volt to the red, and AN1 to the yellow. Also, this one is very easy to connect. Here we have to just be sure that we connect to analog output, this pin, and we connect power and analog output. Okay. Regarding the probe, just connect in this way. Here you can see there is IGR1, so this one will be a label with IGR1. This is a particular version of the board which has also this type of connector and circuitry. And you can contact me if you want this version. The things that this circuitry does is to enable the current on the probe just when there is a reading. This will increase the lifespan of the probe. And then we have this I2C interface, and we are just to connect it to the I2C pin according to the power. And that's it. They are all connected now. We have to connect the Raspberry Pi, and this is very simple because the board has a connector on the bottom. And that's it. Okay, so next step is to power on the system and calibrate the sensors. Okay, so now the system is powered up and all the sensors are connected. On the left side of the screen we have the system interface. Now let's calibrate the sensors. First thing we have to do is to go to the setting page, scroll down and find the sensor calibration button. Here there is a table. We have to be sure that the fields relevant to our sensors are empty and the direction is set to dir as default. So these conditions are met. Let's go back and start the calibration. The calibration procedure is very easy. We will read the two values, one when the sensor probe is in the air and the other when it is in the water, and then we will fill in the calibration table. Let's start with the analog one, where the capacitive sensor is connected, and click Read. This will give a real-time reading of the sensor. Okay, so in the air, the sensor is giving a reading of 3. Let's put it in the water. As you can see, the reading is very stable. It is 1.66. Let's go back. Calibration table. And let's see where is the analog one. Is here. So the minimum is 1.66. Maximum is 3. The scale we put 100 because we want to have a value ranging from 0 to 100. And offset can be left empty. Now we have to set the direction. The automation algorithm expects that the lower value is the drier and the higher value is more wet. As we have seen in this reading, the lower value indeed was when the sensor was in the water. So things are inverted according to the logic of the irrigation algorithm. So here we have to specify that this is inverted, and we choose inv. Then we save, and we go back to check the reading. Let's read analog one. So we see that now it is in the water and it is 100. Let's take it out of the water. And the reading will eventually go to 0 when it's completely dry. Great, so the first sensor is calibrated. Let's move on to the second, which is the resistive sensor, and is connected to analog 2. Let's start to read the values. So when it is in the air, this is 4.99, and when it's in the water, it starts with 2.25. I've seen that resistive sensors are not so stable, at least at the beginning, so it takes some minutes for the reading to stabilize. Okay, the reading seems quite stable now. Let's proceed to fill this value. $100. And also this one is inverted because the reading into the water was lower than the other reading. And let's save it. Let's go back. Let's read it again. So we have around 100. Let's say, take it out of the water. And it's 0. Just I want to clarify that few decimal of error is not a big issue. I will show later the graph that are made by the system in a real life application. Let's go back and also calibrate the other sensors. The other is IGRO1 4.99. Let's put it into the water. Also here we have to wait some time until it stabilizes. Okay. Now let's try also the I2C sensor. 270 out of the water. Okay, let's try this way. Don't want to stay inside of the glass. Okay, so into the water is 512. And as we have seen, when is inside the water, the value is highest. So this one is deer. Okay, the calibration is finished. Next step is to set up the auto watering algorithm. Okay, so far we have connected the soil moisture sensors, we have calibrated them, and now it's time to go to auto watering page and set the watering automation. As you can see, there can be a different set of parameters for each relay. Let's assume that relay 1_1 is the relay which controls the valve for the irrigation, under which there is our moisture sensor. Let's see the parameters. Working mode. If this is set to none, then of course the algorithm will be disabled. We can set to different values, for example full auto, and in this case the irrigation will be fully controlled by the soil moisture feedback. Then we have under min over max. In this mode, this is a kind of hybrid mode between scheduling watering and automatic watering, because normally it works with the scheduling that we set into watering plan. But then, in case the soil moisture sensor goes below a certain threshold, then there is a watering activation. On the other side, if the soil moisture reading is above a maximum threshold, then it stops the watering plan. Then there is emergency activation, and in this case it works only by starting irrigation cycle when the sensor reading is below a certain threshold, and alert only when the sensor reading goes below a certain threshold, send an alert by email if the email has been set. Then reference sensor. Here we can choose which sensor should be the one that controls the irrigation. So let's assume in this case we select analog 1, which was our capacitive sensor. Here we have these parameters. I will show the meaning of these parameters by making an example. So we have minimum threshold, maximum threshold, watering period in seconds, number of watering period, pause between watering periods, and interval for sensor data evaluation. So let's start to say that the system will calculate as a reference value not only the last sample of the sensor, but according to this parameter, it will calculate the average of the samples in the last 90 minutes. It is evaluated in this way to give more robustness to the system. So the reference value is then compared with the minimum and maximum threshold. If the reference value is below the minimum threshold, then a watering cycle starts, and it starts using a first watering period of 100 seconds. After the 100 seconds, the system waits for 45 minutes, as in this parameter, and evaluate the reference value according to the samples in the last 90 minutes. If the reference value is lower than the maximum, then another watering period is started for the second time, and after that, the system waits for 45 minutes, evaluate again the reference value, and compare it with the maximum threshold. If it's still below the maximum threshold, it starts another watering period for the third time. This will be the last watering period in this cycle. Then it waits 45 minutes, then it calculates the reference value again, and if it is above the maximum threshold, then the watering cycle is finished successfully. In case the value is between minimum and maximum, then the watering cycle is finished, but a warning will be issued because the system cannot reach the target value after watering. If the value is below the minimum threshold after all the watering periods, then it means that something is wrong, or in the sensor, or in the valve, or somewhere else, so the system issue an error. And this is the way that the system works. Then we have watering time, and this is the watering time during the day that the system can be activated. Then we have max period between cycles in days. This is a safety feature. If the system detects that there are no watering periods within 5 days, then it will issue a warning and it will start a watering period of 100 seconds. Then valid reading minimum threshold. This is a value that if the reading is below this value, then an alarm is issued. Then there is alert preference, and this one is the mail alert that can be none or warning only or info and warning. Normally I set it on warning only. It means that any warning message will be sent by email. After we finish the configuration, we can save, and it's done. Now I'd like to show you a real example where I use the irrigation, the hygrometer, and the automation in a vase, a quite big vase, where I have the hygrometer and the irrigation is automatically done. Let me go to the interface. And let's go to data. In the data, there is a specific chart that is exactly made to assess the performance of the auto-watering algorithm. Indeed, this chart changes color and type of line according to what is set into the auto-watering algorithm. For example, if in the auto-watering algorithm we link a relay to a sensor, then in this graph they will have the same color. And here we have, for example, here we have the relay, and this one is the sensor associated to this relay. And we can see exactly that when this relay activates, at the same time the reading of the sensor go up. Let's focus a little more on this example. Here I have the sensor reading, then the actuator that activates the irrigation over this sensor. But I also have another sensor. This is I2C sensor, which I'm testing. And as you can see, when the irrigation starts, both sensors will have an increase of the values. Then it's very important to say that depending on the position of the sensor and the position of the sprinkler, then we will have a different level of reading of the sensor. I would say that to set up the auto watering parameters, it's a matter of experience. And for me, it took some time to understand how to set up the parameter first, but also where to put the sensors and which kind of sprinkler have to use. Of course, all of this depends also on the type of plants that you have. Now I want to show you more historical data, make you understand the cycles that are happening in the auto watering. So let's switch to 2 weeks in the past. And this is the data in the past 2 weeks. As you can see, there are a lot of things that I'm testing, but I want to show you the one that I'm using for quite a long time. So this is the balcony side. So let me remove all the other. Here we are. So as you can see, this is the trend of the sensor. And of course, it's going down because there are plants that are taking the water. Then we have water activation, and then the same cycle start again. You may notice this oscillation, and as I explained before, this is a resistive sensor, and this oscillation have exactly the frequency of 1 day. And I checked with the temperature, they overlap quite completely. It means that this effect is given by the daily temperature change. As you can see, this is set to provide the same amount of water for each irrigation, but as you can see, the period between irrigation changes. And this is normal because sometimes the weather is more cloudy, sometimes there is more sun, it's more windy, so the soil changes the humidity at a different speed. Hope it was clear, and if you have any doubt, please feedback to the forum. I put the link into the description of this video, and thank you for watching.